I should say good morning, good afternoon, or good evening for the audience from different locations all over the world. Welcome to the Centaur webinar series. The topic is about brain-computer interface. This event is hosted by Center of Autonomous Robotics at University of Bath. My name is Dingguo Zhang, and I am the Deputy Director of Centaur. Today, I will chair this seminar. Centaur is a new research center, and it just has a history of 1 year. Centaur targets cutting-edge research of robotics, such as rehabilitation and assistive robots, human-machine systems, autonomous vehicles, artificial intelligence, and advanced control in robots. Centaur provides PhD program and master program for the excellent students all over the world. There are two sponsors for this event, Brain Product UK and Nueco China. Thank the two companies for the support. Today, Professor Bin He from CMU will give a talk. The title is Dynamic Brain Mapping and Brain-Computer Interface. Let me give an introduction of Professor He at first. Bin He is the trusted professor of biomedical engineering, professor of the Neuroscience Institute, and professor by courtesy of electrical and computer engineering at Carnegie Mellon University. Professor He has made significant research and education contributions to the field of neuroengineering and biomedical imaging, including functional biomedical imaging, non-invasive brain-computer interface, and non-invasive neuromodulation. His pioneering research has helped transforming electroencephalography from one-dimensional detection technique to three-dimensional neuroimaging modality. His lab demonstrated for the first time for humans to fly a drone and control a robotic arm just by thinking about it using a non-invasive BCI. He has contributed significantly to neuroengineering education, including editing the first textbook in neuroengineering and led multiple training grants in neuroengineering. Dr. He has received a number of awards, including the HPOE Biomedical Engineering Award, the HPOE EMBS William Morlock Award, the Academic Career Achievement Award, and the Distinguished Service Award from the HPOE EMBS Society, and also other important awards from the well-recognized organizations. Professor He served as the past president of the HPOE EMBS Society. He is also the chair of some important international societies. Professor He served as the editor-in-chief of HPOE Transactions on Biomedical Engineering before, which is the flagship journal in the field of biomedical engineering. During the past 3 years, He served as the head of the Department of Biomedical Engineering at Carnegie Mellon University. He made a contribution to the department and had lots of achievements. I finished the introduction of Professor He. Dear audience, during the talk of Professor He, if you have questions, you may type the question in Team. This way is more convenient and efficient. After the talk, Professor He will read your questions and answer the questions. Professor He, you can share your screen and the talk now. Thank you.
Everything looks good on the screen for the share?
Yes, yes.
Okay, great.
Yeah.
Well, thank you, Dr. Zhang, and thank you for your invitation and an introduction. It's a great pleasure for me to be speaking today with a group, and the webinar series looks fantastic, and I'm looking forward to hearing other speakers talk down the road. I believe that I probably would have about 40 minutes time to presentation and reserve about 10 minutes for the discussion and after the talk. Okay, so my presentation today is going to focus on two aspects. I understood this is a BI and a webinar series, but I'd like to start with dynamic mapping. And one of the important tools that my group has used that for facilitating BCI research. And then I'm going to switch into the non-invasive sensory motor reason based and a brain-computer interface. So this slide illustrates one concept, that is our brain activation is a spatial temporal process. So in this functional MRI map, as you can see here, that the specific activation of a regional brain region is distributed in three-dimensional domain. So in a sense that a different kind of brain activity is located in different locations, we need to find out where these brain activation is located. This is one aspect. Another aspect is if you look at this blue guy, which shows temporal evolution of the both MRI signal, from here to here, it's about 10 seconds. So in a sense that functional MRI, while it's a very precise spatial localization of brain activation, it does not provide sufficient high enough temporal resolution. And this purple color shows EEG signal, which gives, or EEG, or I mean, any kind of electrophysiological signal is going to give high temporal resolution. But on the other hand, EEG, particularly scalp EEG or scalp MEG, do not provide high enough spatial resolution unless we do something. This slide is a little bit basic, basically is describing the relationship between what we can observe clinically or in an experimental setting, that is scalp EEG or scalp MEG, with what's happening inside the brain. And you can see it when our brain carries a certain, conducts certain task or has a certain functional status, different neurons inside our brain is going to be recruited for being activated for this particular stage or task. This transmembrane current, then the current is going to flow, generating primary current flow inside the brain. Our brain itself is a passive volume conductor. So if you have a current because of driven by neuronal excitation, then there'll be current flow and inside the brain, which is going to develop a potential difference. If you put an electrode over the scalp, that is the EEG. If you put the coil outside, that will be the MEG recording. The relationship between the neuronal excitation and the scalp EEG or MEG can be represented by such kind of simplified linear and system equation. So by solving this and a linear inverse problem, we may obtain the source distribution inside the brain corresponding to a measured EEG or measured MEG. So this approach we call electrophysiological source imaging, that is to starting with the scalp EEG or MEG with aid of structure MRI, taking this anatomical information, and we solve the source imaging problem, we could obtain relatively high spatial resolution and definitely high temporal resolution and source distribution inside the brain. There's one concept I want to mention in the recent NIH Brain Initiative workshop. A question came up, that is that the EEG source imaging is start from EEG. So does that mean the information content of the EEG source imaging essentially should be the same? Because if you do not add anything else, even though you do source imaging, solve the inverse problem, you should not gain additional, except maybe visually it may look better. And my answer to this question is that actually is not, because you can see that unless you do not taking this MRI structure information, once we take this MR structure information, we provide anatomical physiological constraint to the source distribution, normally in the cortical current density. If you assume that the current density is flowing perpendicular to the local curvature of the cortex, you add a lot of constraint information that is personalized based upon this particular measurement. Therefore, EEG source imaging does contain information content that is beyond what's contained in the EEG recording. The next, I want to show some example. That is one typical example of dynamic EEG source imaging or mapping is in the application to epilepsy, because as what many of us know, this illustrates EEG. This is resting state is normal. And here seizure start. Once the seizure start develop, you can see there's a very large oscillation that generated by the epileptic network. Now, a question is that how we're going to deal with the seizure. In the world, there are more than 65 million people and suffering from epilepsy. 1 out of the 3 epilepsy patients cannot be treated by medication alone. Therefore, we have to do something. And if you cannot treat by drug, and usually is if you can find out where the seizure comes from, and if you can safely remove the seizure generating tissue, surgical removal is one of the clinical options, or the neuromodulation. Regardless, we need to find out where the seizure comes from. So here is a clinical and routine, and usually you go to see a doctor, do an EEG, MRI, and due to the spatial resolution limitation of scalp EEG, as what we discussed, and normally in many of the patients, a invasive procedure called invasive intracranial EEG procedure is being performed to quantify, localize the seizure onset zone, so more accurate surgical removal can be occurred. Now here, this application of the EEG source imaging to this problem, the concept is we are attempting to use non-invasive EEG recording and perform the EEG source imaging, and sometimes with the aid of further functional connectivity and analysis to find out where the seizure is located and or is a seizure onset zone is located, and then provide that information to neurosurgeon to guide a successful neurosurgical and operation. Now, I want to show just a couple slides of our recent results on this procedure. And here show a typical example interictal spike, which is electrophysiological and events between seizure, and which is commonly recorded. And what we do is we record this interictal spike. We perform source imaging and using a new and source imaging algorithm, which I will not get into the detail. And then we compare with surgical resection in the patient. This green dye show where the resected area, and if the patient was seizure-free, then that means this green color illustrates that surgical resection will contain where the seizure, where seizure-generating tissue is supposed to be. Another is using invasive EEG recording, and these are intracranial EEG, each dot, and the red color shows the seizure onset zone. So we compare with the seizure onset zone and the surgical resection, and from the non-invasive EEG. This is our non-invasive EEG source imaging result in 3 typical examples. The right column shows clinical ground truth. In the middle column show the overlapping of both, for example, like in this case, the dark color brown and the reddish color shows source imaging, and this light green shows the surgical resection. And here is showing that this is seizure onset zone identified by invasive EEG, and this is non-invasive and source imaging result. Now, the group statistics are just one piece of information I want to draw your attention is the overall average in all the patients and their localization error is about 17 millimeter, which is not big, but anyway, this is 17 millimeter. The next in the group of patients, we record seizure, and we perform direct seizure imaging, and all their illustration is similar as the previous, but if you could look at this localization error again, you can see the overall group average localization error from the estimated source using source imaging is a decrease from 17 millimeter to 6 millimeter, which show a great improvement that if we are able to directly measure seizure and localize the seizure, that will provide a much better result. And another interesting result is so here, if you look at this result localization error, this means seizure-free patient. This is non-seizure-free patient. That means interictal spike source imaging works quite well in the seizure-free patient, but it did not work well in those patients who were not seizure-free. But if you look at the direct seizure imaging, you can see that there is no difference, essentially no difference between these two groups. So, which indicating that for those patients who were not seizure-free, direct seizure imaging may provide a lot of clinical benefit. This video just illustrates the graphic illustration and how this technology would work. And you can see on the bottom is the average and the field power of all the EEG over the scalp. And here is illustrating dynamic animation show the source imaging. This is intracranial EEG. The red color show the seizure onset zone. So if you compare this, you can see that this dynamic EEG source imaging could provide a fairly good and non-invasive imaging outcome overlapping with the known and the seizure onset zone based upon the invasive recording in this patient. So I want to show one more and another approach along this line is not just to do the seizure imaging. We found that there is a new biomarker called the pathological HFO, high frequency resolution and oscillation, which means that you have the high frequency oscillation happen with interictal spike at the same time. And then we perform source imaging. We found that that result can significantly enhance and epilepsy localization. This is one example compared with surgical resection. In this patient, you can see this is green color is a resection, and this brown color shows the HFO and source localization result. On the right side is the same patient, and this broadly spread out is source imaging result from interictal spike. In another patient, we compare with intracranial EEG and the recording, and once again, you can see this pathological HFO localization result is a much more better consistent with SOZ, while the spike result is relatively diffuse. I just want to take this opportunity that if some graduate student and in this webinar that I want to mention that I don't have the time to talk about the EEG or more electrophysiological connectome approach, but we do have a MATLAB open source toolbox e-connectome, and which you can easily find out by Google, and every line source is open, and everybody is welcome to use this. So I guess now I want to switch to the brain-computer interface, which I know that is of interest to many of you. And this slide illustrates basically, and I believe everyone or most of us know about the brain-computer interface. And one thing is you could use invasive recording if you put the electrode to record a neural spike train, local field potential, or ECOG, or you could use EEG as what we discussed to get a scalp EEG. So my talk is going to focus on non-invasive EEG-based brain-computer interface. You could extract the signal and extract the feature and control a device for replacement or restoring, enhancing, supplementing, or improving human function. Particularly, in my talk, I will be focusing on motor function. Now, why we want to do this? I want to give you some statistics based on USA alone, and I know different countries would have different number. In United States, more than 5 million people are paralyzed. It costs United States every year more than $40 billion to treat spinal cord injury, a single disease alone. So this is really a big burden to the public and society, and just not to mention there are many other diseases. This is the rough estimate and based on information available, which is a few years old, that say what are different kind of source of the paralyzed patient. You can see the top two are essentially spinal cord injury and the stroke. These two diseases occupy about 60% of the patient, plus some other disease as well. There is a clinical need to do rehabilitation of the patient, to help the patient be independent, and to help the patient to communicate. So, and the BCI can be used for physical therapy, and BCI could be used to develop neurorobotics, or BCI could help with the text and speech prosthesis. So now the next is let's come say that what is a BCI, although we all know about the BCI already. Okay, you have a brain, you have a computer, and here you have a device you want to control. And we are focusing on, say, through non-invasively decoding user intent in real time. BCI bypass traditional neuromuscular pathway to provide alternative routes of communication and action. Now let's take a little bit more detailed look here. And one specific thing, certainly you have many ways to accomplish that. And particularly my work and my lab's work and focusing on something and is based upon sensory motor reasons. So as you can see in this illustration here, that by imagining certain movement action, and you will generate a detectable sensory motor reason, and you detect that you control a device. And more intuitive explanation is shown in this slide. For example, and this is a protocol we use very often in our lab, is you can imagine moving the left hand, right hand, or both hand, or maybe none of them. And that is going to give us a command to control a device. And if you record EEG, if you extract the topography, you will see this very unique pattern and over the scalp corresponding to left hand, right hand, both hand imagination. So I will give you a few examples and for our experience along this line for the sensory motor reason. The first work, which now time flies, and now is already 8 years, I cannot believe it. And we thought we just did it, but that is to move the non-invasive sensory motor reason-based BCI from cursor movement to fly a drone in 3 dimensions. So in this particular case, this work was done at the University of Minnesota when I was on faculty there. And you can see that this is a college gym, and there is a quadcopter or drone, and which is controlled by this individual wearing an EEG cap. And the person can see the drone. We set forward going velocity. So the drone is keep going forward if there's no control command received from the subject. And subject is going to turn the drone to the left by imagining moving their left hand, turning to the right by imagining moving the right hand, and imagining moving both hands to lift it up, and imagining none of their 2 hands are actually moving to bring it down. So this is one of the examples to show that a BCI can control a robotic device in 3D space using a quite simple and actual motor imagination action. The next, what we do is we say, okay, what about to control a robotic arm? In this work, and we use a similar protocol, but to control a robotic arm, and subject is by imagining moving the left hand, right hand, both hands and then none of them, you have 4 control commands in total to reach the Lego on the desk and then grab it and bring it to a location on the shelf that at user's choice. And of course, this video was taken when we still provide a visual aid on the right lower corner, but in response to one of the reviewer, when the paper before was published, we repeated the experiment without such kind of visual aid, and results were essentially the same. But nonetheless, I mean, the video showing that what this is being done. Now, of course, this robotic arm control, even though in 3D space, it was a quasi 3D. Essentially is we divided that into 2D plus 1D and control. So essentially that use 2D, you find in the XY plane, and then you control the robotic arm on the Z direction. So it's not a true meaning 3D control. The moving forward and recently, and we have further our experimentation, that is to accomplish the goal that the previous robotics arm control is essentially a center out. So you have starting point, you go to a end point. So from one point go somewhere else. There was no continuous control of a robotic device as shown in the previous work. And in this recently completed work, what did we do is actually we did 2 things essentially. One is on the user learning side, we introduced a continuous pursuit and a task. That is quite often used in the invasive and intracortical BCI work, either in monkey or in human subject. And you can see that the robotic arm can be controlled continuously. And in this case, we introduced this continuous pursuit as well, and for the EEG-based and BCI. The second thing is we introduce a machine learning approach in addition to other spatial and the temporal spectral analysis. We use the EEG source imaging. That's the one I described in the beginning of my presentation. So we take an MRI of the subject and we get an EEG and we record a 128 channel EEG and we solve the EEG source imaging real time and then to control a robotic arm. So let's look at how this work is going to look like. So in this case, you can see this is a 128 channel EEG cap. It's an EEG recording, and the source imaging is performed in real time. And we have this ball, this circle is controlled by the random generator. So it is randomly moving around on the computer screen. The subject is controlled just by using motor imagination as what we described already to control this robotic arm and in a continuous way. So it's no more like the cursor movement center out starting from the beginning, middle of the screen, and then go to the right or go to left or up or down. In this case, you continuously, you decode and control this robotic arm to track this randomly moving object on the computer screen. So this is, to our knowledge, the first example to demonstrate non-invasive BCI to be able to continuously and track an object, although it is in the 2-dimensional space. And certainly it will be very exciting if similar thing can be accomplished in the true 3D space. So let's try to see the benefits and the pitfalls of sensory motorism-based brain-computer interface. Their pros are clearly, we all know it's non-invasive and intuitive. It can be done for continuous control. But the limitation, and usually for those who experienced with the sensory motorism BCI would know it does take quite a long training time. For example, in our experience, either the drone control, robotic arm control, and usually it would minimum take about 10 sessions for the subject to gain the skills. And usually session, because it's easy, you have to do the capping, you finish up. So it would take about 2 hours for each session. And of course, we usually recruit a college student as a volunteer. So that means this student would only wish to come once, maximum twice per week. So it would, if once per week in general, it would take you 10 weeks. It would be interesting, although we never tried. What about if you recruit someone, you concentrate, say, for a day long or 2 days long training, see if that you can pick up the skills. I hope someone is going to do it. We will see in the literature in the future, but we don't know. So, and anyway, it takes quite a long time to train the subject. And another is there's a big variation among the user skills. So from subject A to B to C to D, their skills is vary. Probably this is going to be similar case in many other cases, in many other techniques as well. And also there is about roughly 15 or sometimes could be up to 20% subject that is being studied. These people is going to show inefficiency. They're not doing very well with these sensory motor rhythm-based BCI. Now with this, we have been looking into one particular neuroscience hypothesis. And I want to mention that this hypothesis actually is not a theory-driven. It is rather based on our experience. And in our lab, we've been looking into large number of human subjects. And now one of the very interesting, certainly we do group statistics in all the study we do, but the best performer or best subject who show really great. And we interview them and we found they are always a meditation or yoga practitioner. So from there, we started to ask a question that whether the meditation plays a role to enhance a BCI skill. So here actually is a theoretical backup, even though it's not direct. On the left side is showing the brain regions which are considered to be important that involved in neurofeedback control, neurofeedback learning, and neurofeedback reward processing. And the right side is showing the brain region which are responsible or considered to be important in mindful meditation. So even though it's not a one-on-one correspondence, but you can see that many brain regions are actually involved in both process, okay? In either neurofeedback control learning, reward processing, or in the mindful and the meditation. So our lab actually quite a time ago, we've been looking into the effect of mindful meditation, or more specifically, is the mind-body awareness training on the BCI. Our first work is looking into long-term practitioner. So actually when we publish, we notice there's another publication in the same year. In this particular work, which is illustrated on the left side, it's a very simple task. We recruit 36 human subjects, 12 people with meditation of 1 year or longer, which is the blue color, and the control, 24 control, and they have virtually done nothing about the meditation except 1 or 2 sessions in their life. And we ask both group of subjects to start a control and cursor to left or right, and then up or down. At the end, we found that the meditation subject, 2/3 of them can complete, while the control, only 1/3 of them is able to accomplish, which illustrates that a significant effect on mindful meditation or yoga to help subject to perform BCI task. Now, the next question would be, what about a subject who were not a long-term practitioner of yoga or meditation? Can we recruit them, give them a mindful meditation training, and to help them to gain the BCI skill? So for this protocol, what we've been doing is we recruit a total of 144 subjects. And it was an experiment that lasted for 3 years. And at the end, and only 76 subjects finished everything, because we started with a baseline BCI session, and then we randomly select half of subject to send to an 8 weeks meditation class. The other half of subject is being put into waiting list. After 8 weeks, we bring everybody back to go through a series of BCI sessions from 6 to 10 sessions. So the entire process lasted for about 4 months per each subject, and therefore some of the subjects really lost the interest and they dropped out. So out of the 76 subjects completed, we were able to obtain complete data in 62 subjects, and we've recently finished and studied this group of 62 human subject data. Just want to mention brief explanation what these 8 weeks and people and was sent to. There is a standard training class called mindfulness-based stress reduction, or MBSR. This is 8 weeks and once per week. And then in the middle, there will be a day-long and a retreat. This is a very standard meditation class, okay? And then what we ask a subject to do is a relatively simple task. So it's a center out, you control the cursor to the left, right, up, down, and it's 1D, 2, and a 2D. Essentially, that is the task. Now, among the 62 subjects who completed everything, we have completed data, and this slide shows a summary. On the left side shows effect of the mindful meditation, the training. That is a standard breath counting and task. So what we found that there is statistically significant difference in the meditation group before and after the class. And there is statistically significant difference between the control and the meditation class and after the intervention. Here is baseline normalized performance. You can see that the meditation group, which illustrate in this red color here, outperforms the blue color, which is the control group, and both in terms of performance and in way of the learning. On the right side, we perform statistical analysis, and we found although the meditation group do better than the control, but there was no statistical difference between the left and right control. However, there's statistically significant improved performance for the up-down control, and most importantly, for the 2D control. And here illustrate one another and experimental evidence that why there would be such kind of difference. So this is one example in terms of the topography and in the group average for the control group and the MBSR, the meditation group. This is for general, which is what we would observe, and for over the scale. But on the bottom is saying after the meditation, you can see group average in these meditation subjects, the electrophysiological characteristics showed significantly altered pattern compared with the control group, which may explain why. That means short-term 8 weeks meditation can introduce some plasticity and introduce some change in our brain. That's why make this outcome of the BCI control and improve. So we have brain computer and a device. In this particular example, we just shown while the most work, and we know that usually focus on the computer or machine learning. In this very recent work, we demonstrate that there is a role, and sometimes could be important role, the brain can play in brain-computer interface. That is MBSR, or the meditation can be used to improve BCI performance. Now, the next question we want to ask along this line is how can computer to play a role to improve the performance? And specifically about this group of human subjects we studied, we look into the deep learning decoding to see if the deep learning with artificial neural network can be used to improve the BCI classification task. Now, there are many review papers that we wanted to mention that we cited this recent review, and there are many recent effort actually in the literature to use deep learning to assist the brain-computer interface. Now, while these work are all very, very interesting, and certainly before we conducted the work here, and we analyzed this existing literature, we found that most of these published work were tested using small data set. And it's a trial-based classification, and it's focused only on motor cortex. So because of that, and we do have one of the largest SMR and BCI database to our knowledge, and it's also continuous classification. It's not just motor cortex alone, but we did record the entire overall scalp with high density EEG. So with that, and we performed a study. We did not come up with a new deep learning architecture in this particular work. Rather, we just adopted a recently published deep learning neural network, and which involve a temporal convolution. And we just adopted this particular network and to analyze our data. Now, this is the summary of the results. When we analyze, I just want to explain this color. This gray color shows the online, which is the online behavior outcome. That is our experiment we just discussed. Now, this pink color or red color show the motor electrode only. That is, there are 10 electrodes covering the sensory motor rhythm on the both hemisphere. We use these 10 electrodes covering the motor cortex, and we use these 10 electrodes to train the deep learning neural network and then perform the offline classification and then compare with these online. This blue guy showing is deep learning based, but we use all 62 electrodes. So the high density 62 electrodes were all used to train the deep learning and to get the result. You can see here that in the left or right cursor control, up and down cursor control, and 2D cursor control, in all the case, the deep learning classification actually improves the online classification. And the more electrode you use, actually the better. That's the simple and message from this work. Now, in here is, we show that this particular and deep learning and the network classification, the improvement is significant if we would use all electrode, which illustrate is this blue guy. Okay, and if we use all electrode, then in all the tasks, the performance was improved compared with online classification. Now, if we are going to use a motor model only, that is a 10 electrode covering the motor cortex, plus deep learning, and we found that the improvement were observed in the left or right control and up-down control, but not in the 2D control. So this is essentially what this experiment and we found. So in summary, I think my time is coming up. So what we discuss is can be summarized in the following few bullet points. The EEG source imaging enables dynamic imaging of brain activity with high temporal resolution and good spatial resolution. EEG-based BCI allows non-invasive decoding of the mind and controlling of robotics or device. And mindfulness improves BCI performance by increased control of neural activity in the alpha band. By the way, I mean, you can certainly look at the beta band, gamma band, or theta band, but our work is in the experiment I described, we only observe significant improvement in the alpha band. And furthermore, deep learning improves the BCI classification accuracy, and also this offline analysis suggests that the whole scalp coverage EEG, which means beyond the motor cortex, may provide enhanced performance, particularly in the 2D cursor control case in this study shown. I want to mention that the work I'm presenting today are group effort. The left list are number of the people who are current or past student of postdoc in my lab. Right side is a faculty collaborator and involved in the work I'm presenting. And the work is supported by NIH and NSF. And I want to take this opportunity to mention that the third edition of the neuroengineering textbook was published about 8 months ago by Springer, which is co-authored by about 24 of leading experts in neuroengineering internationally. So if any student would have interest, you may find this book and freely available from your university library. Thank you very much, and I would be happy to take any question, if any.
Thank you, Professor He. Thank you for the wonderful talk. I think some audience have questions. They have typed the questions. You can read them from Xingao. You can read the question and give some answers for him.
Dr. Zhang, would you mind to read the question for me? Because somehow I get a little bit the technical challenge on my screen for the, because of Zoom, you know.
Okay, okay, I can read the questions. In the current non-invasive means, if there is a way to improve the information transmission rate, except the decoding algorithm. In other words, if there is a possible way, except the existing way to get more information by a non-invasive approach. This student just asked if there is some good way, except for the algorithm, that can also improve the performance of non-invasive BCI. Can you give some alternatives?
Thank you. By the way, Dr. Zhang, now my Zoom, the chat come back. Okay, I can see myself. Okay, thank you very much. So let me get this first question first. This is an excellent question. I think that people like us working in BCI field, you always want to find out some new way. And certainly, I think that lots of effort and is being put in the decoding algorithm. To directly answer this particular question, I don't think that there is an inclusive answer, but I just want to give you one example. In our work in this mindful meditation experience, that is showing one example other than your improving decoding algorithm, but actually you can bring in the neuroscience factor. That is, in this case, you are changing the central nerve, changing what's happening inside the brain while keeping the algorithm untouched. All right, so that could also improve the performance of the BCI. And that is non-invasive as well. And I don't know if that answers your question here, but I think that is one example. Okay, so maybe let me go to the next question here. Is that possible to reshape EEG by using adaptive characteristics of organism? For example, external device that use a fixed control mode can move when receiving a signal. What we do is not decode and control, but constantly train to make the brain familiar with this control mode to achieve a more natural control. This is an excellent point that being brought up. That is, it's not static, but adaptive. I believe that although I didn't do a literature survey recently, I believe some of the groups is doing this in the sense that in this decoding or in this learning process, you could have static or you could have adaptive. You can adaptively updating the parameter or even the algorithm and during this process. And although that I think we need to see something more outcome, but this, I totally agree. I think this would be a very ideal because our human brain is adaptive and this process is, just to give one example, that even in sensory motorism BCI, the parameter you choose and can be adaptively updated. This is, we did not systematically study it, but we did practice that as well. All right, next question. For the same brain activity task, such as motor imagination, will different participants have different results because of their different understanding of the task semantics. For example, other people have different understanding of the term thinking about left hand movement. Is that possible that some subjects' EEG signal decoding efficiency is low? This is another excellent question, and that is exactly why I mentioned that there's a 15 to 20% subjects, sometimes they may not perform well. I just want to mention that according to our experience, I give you one experience, say the two tasks we practice, flying a drone or control robotic arm. So left hand movement, right hand movement, what does that hand movement entail? Different people are going to have different understanding. Different people may have different kind of induced EEG signal. Therefore, the control signal you can extract may differ from subject to subject. And our experience is actually we practice that in each individual subject to first in a very simple cursor control and setting to make sure that, for example, move left hand, right hand in subject A is going to maximize the control signal that we can establish in a very simple testing scenario before we try in the challenging and the situation. Because in one subject, maybe they were thinking about this is the left hand. Another person will be thinking this is a left hand and movement and whatever it takes. And it doesn't matter because our goal is to train subject to generate strong enough and control signal to accomplish the goal we want to accomplish. All right, next question. What do you think the best way to eliminate the calibration stage in BCI? Well, it's a good question, and I assume the calibration, if you talk about a more rigorous assessment, I believe that we do need a baseline and session. And the calibration, if you're saying that to refine the fine tuning, I don't have a simple answer, but I believe that the calibration is going to further fine tune to improve the performance. But even though you don't do that, and the sensor motorism in most of the people, it will work pretty well in general. Okay, all the calibration can further fine tune and improve. Next question, have you compared your deep learning based accuracy with FBCSP and EEG-NET? Wonderful question. Actually, in their paper we just e-published in Journal Neuroengineering, we did compare with FBCSP algorithm because we consider FBCSP algorithm or general CSP algorithm is a very successful benchmark because you have to compare with benchmark. And for our experience with this particular and deep learning net that we implemented and to try, and the deep learning actually performed better than this FB and CSP. We also learned the EEG-NET from one of the journal reviewer, and unfortunately we did not notice that earlier, and that there's an excellent performance network about EEG-NET. But since we completed the work, student graduated already, he's in Stanford now. So we did not have time to compare with EEG-NET. So this will be interesting and to see that which one would work better. And there is an excellent literature about EEG-NET in the literature. All right, next question. What is the minimum number of electrodes or spatial resolution that suffice for source imaging? For instance, 32-channel EEG, 122-channel, 256-channel. Could we benefit more from high-density EEG acquisition, such as 256-channel EEG in source imaging and classification? Well, excellent question. I like this question because, I do source imaging throughout my career. So I really love people to ask a question like this. But being said, I think there's a trade-off. And the more electrode in general and would be better at a certain range. after you're reaching at a certain number, it probably is going to be saturated. So in a sense that just hypothetically, if you're going to use 1,000 electron, would that give you drastically better performance? I don't think so. The reason is this has been pursued by some other researchers because you have finite signal to noise ratio. This effect of noise is going to impacting the performance of source imaging. So come back to specific question. We try 128 channel in our science paper, and I would think that maybe I would try 64. We have not tried 32 channel EEG directly for source MCI, but I'm not very sure if channel EEG will be needed because it will take a lot of time for you to get that EEG, and also there seems no very strong scientific evidence to show that 256 channel EEG is going to significantly better perform compared with 128 or even fewer number of channel EEG. But 32, usually there is international guideline about how many EEG channels needed. The recommendation is at least 64 channel would be designed to do EEG source imaging, and certainly, and if you can get more, and it will be better for in general. But I'm not very clear if 256 is needed. Come back to the second question. It is known that a multi-imaginary has a relatively high rate of BCI illiteracy. How do you tackle the issue in your research? This is an excellent question, and that we refer to about 15 to 20% subject did not show efficiency in BCI. I think this mindful meditation really is in one way address that challenge. I guess I have to hurry up given that it is running out. And the question is, I heard that meditation training can enhance cognitive control ability. So can we make a conclusion that it is enhanced cognitive function that improve the BCI performance? If this is true, I think a part of meditation, other cognitive function approach can also be improve the BCI performance. This is an outstanding question, and certainly do not know exactly why the meditation can help improve the BCI performance, but I think certainly I would agree that yoga or meditation may not be the only practice or way to improve the cognitive improve. I don't want to use cognitive function. What it would be, it will remain to be seen. And then my personal take about the intuitive understanding why meditation yoga can improve the BCI performance is we use the sensory motorism, it's motor imagination, and so the people going through the meditation, actually they develop the capability to pay attention, and which is how enhance their motor imagination and the task. So that explain, but once again, their mechanism need to be further looked out. Next question. John, should I keep it going, or is that okay? You are muted, Dr. Chang.
Sorry, if you still have time, maybe you just answer 3 more questions. I wonder if you can.
Yeah, sure. Yeah. Of course, we'll do.
Sorry to take your time.
More questions. Yeah, I will try to make it brief.
Okay.
How long the improvement MBSR lasts? How did you calculate the online? Okay, well, the online accuracy is because you have a cursor generated and you hit, and it's success or you fail, and that is by default we can. The effect MBSR, as what I mentioned, after MBSR, we brought back subject to go through 6 to 10 sessions, and that usually occur in about 1 to 2 months period. So it could be up to 2.5 months. Do not bring them back and a half a year later. Next question. I have one question about the seizure onset detection topic. As you group shown that it's possible to localize the seizure focus on the cortex. If it's possible to detect the seizure focus that are located in the deeper brain structure, how about the localization accuracy? Is there, if there are remaining problems to be solved in the current stage? It's an outstanding question, and source localization and the best in for the cortical source localization, and for the seizure localization, yes, it has been big challenge that we were able to get a deeper source. But I just want to mention that recently there are a few groups from Europe and the United States, to my knowledge, were 2 papers published in Nature Communication in February 1 day, and our paper in Nature Communication April last year, and also the Mass General group, and there are several groups recently started looking at the source localization of the deeper brain. It would not perform as good as in cortex, but on the other hand, these recent work demonstrate they are able to get the deep brain source as well. So things are improving, and it's still a challenging and ongoing task. I believe the next, and which is supposed to be last question, according to Dr. Zhang. Thank you for pointing out that it's not enough to focus only on pattern recognition. The brain is an essential component in the control loop and is often neglected. In all the studies you presented, did you only look at alpha, or did you find other relevant changes as well? Excellent question. As what we know, alpha rhythm is the rhythmic band of the EEG signals, our brain activation. We did not exhaust the search, but we did look at the different kind of and a band for some of the study. And our experience is that the alpha rhythm seemed to be most helpful in our study. And I do notice that there are other groups, for example, the Graz group and Houston group reported very interesting result using low frequency oscillation signals. And then certainly some other group may use beta or some others. But our experience is we found that the alpha rhythm work is a very, very effective. It's not conclusion. It's just our experience so far. Thank you very much. And according to Dr. I guess.
Yeah, thank you again for your wonderful talk and the as to all the questions. I'm sorry, due to the time limitation, you cannot answer all the questions, but I appreciate that you give the wonderful talk today. And
thank you. It's my pleasure. I apologize to colleagues. I saw there are still 2 questions unanswered. If you still have, feel free to send me an email. I'll be happy to respond by email. Thank you.
Yes, everyone for the attendance. And next talk is on 10th June. So I hope to on 10th June. The talk is given by Joe Smith. Then let's close this webinar. Thank everyone. See you next time.